Okay, lesson 3.3 is on the characteristics of polynomial functions in factored form. So a lot of factoring, coming back and looking closely at the characteristics of a polynomial function that you can tell when it is in factored form. So here you have the definition of a polynomial function, and you've seen it earlier. That's like the textbook definition where you have, different terms, one or more terms, and you have coefficients that are all real numbers, and you have exponents on your variables that are always positive integers, and this n, which is the highest value or the highest degree, is the degree of the polynomial. We know these things. We also going to look at a family of polynomial functions. What does that mean? Well, a family of polynomial functions is a set of polynomial functions whose equations have the same degree and whose graphs have the same characteristics in that they have the same shape, the same number of zeros, and so on. So we're going to kind of try to find characteristics that help us to identify right away which family a polynomial function belongs to. So for example, if I gave you a polynomial function, let's say in factored form. So example, a polynomial function in factored form. Okay, so I'm just going to make one up here. Let's say f of x equals some leading coefficient a times x minus x1 times x minus x2 times x minus x3, and so on and so forth, and the last term is x minus xn, then these x1, x2, x3 are all the zeros, right? x1, x2, x3, and so on to xn are the zeros of the function, right? So if I gave you a function g of x equals a x minus x plus 3 times x minus 2 times x minus 1, what would the zeros be of this polynomial function? It would be -3, +2, and +1. You could tell because it's in factored form. So that's something that we will be looking at in this lesson. We're going to look at how to determine zeros. Okay, let's take an example. You already know this, but let's just review it. Let's say f of x equals 4 times x plus 3 times x minus 4 times 2x minus 3. Let's say you factored a polynomial. We haven't yet learned how to factor them, but we will be looking at that in this unit. But if you had it in factored form and you had to tell the zeros, what would you do? You have to set f of x to 0. So you set this to 0, and so you solve for this to find what values of x would make this function 0. So this function can be 0 if either this term is 0, or this term is 0, or this term is 0. So x plus 3 could be 0, or x minus 4 could be 0, or 2x minus 3 could be 0. So we solve these equations. If x plus 3 is 0, that means x has a value of -3. If x minus 4 is 0, that means x has a value of 4. And if 2x minus 3 is equal to 0, that means 2x equals 3, x equals 3 over 2. So what are the zeros of this function? The zeros are -3, +4, and 3 over 2. Those are the values that make this function 0. Let's take another example. Let's say you have a function g of x, which is equal to -x plus 1 squared, x minus 5, and x minus 6 squared. What do you think the degree of this function is? So this is x squared, so that's 2, plus the 1, 3, plus another 2 here, because when you square this, you'll get x squared. So 2 plus 1 is 3, plus 2, 4, 5. This actually has a degree of 5, okay? When you expand it, you'll find that the degree of this function will work out to 5. So what are the zeros? Well, set g of x to 0. and you can find that it can be 0 if any of these are 0. So x plus 1 could be 0, or x minus 5 could be 0, or x minus 6 could be 0, which means the function is 0 at x equals -1, or x equals 5, or x equals 6. So the zeros are -1, 5, and +6. All right? Let's try an example. Determine the family of functions with a degree of 3 and with zeros 5, -3, and 2, and determine the specific family member which passes through the point -1, 24. So when you say family of functions, it means just give me the function, what it could look like without giving me the a value. And then tell me the a value by, if I gave you a point like this in part B, can you tell me the exact function? Okay, so part A is very general. So we're going to say f of x equals a. We don't know what the leading coefficient is because it has a 0 that's 5. So x minus 5 is a factor. Because it has a 0 that's -3, that means x plus 3 is a factor. And because it has a 0 that's 2, that means x minus 2 is a factor. So this is the family of functions, okay, that have these 3 zeros. And you can vary the a value and get different functions that have the same zeros but have different end behaviors based on what the a value works out to be. Okay, so that is the answer to part A. And in part B, you're going to substitute the point that they gave you in the question, which is -1, 24. When the x value is -1, the y value is 24. So 24 equals a times -1 minus 5, -1 plus 3, -1 minus 2, and work that out to solve for a. So 24 equals a times -6 times 2 times -3. 24 equals 6 2s are 12, 3s are 36a. We divide both sides by 36, and a works out to 2/3 in lowest term. So therefore, the specific family that has this point -124 will be f of x equals 2/3 x minus 5 x plus 3 x minus 2. Okay. Now, we have to know what is meant by the word the order of a 0. So if I give you a function like this, f of x, here's an example, f of x equals x plus 2 squared times x minus 1. You can tell that if you expanded this, you would get x squared here, and you would get x here. So the degree of this function will be 2 plus 1, which is 3. So it's going to have, it's an odd degree function, but it's going to have an order of 2 for this factor because it's raised to the power of 2, and order of 1 for this factor because it's understood to be raised to the power of 1. Okay, so the order of a 0 so if I say, what is the order of the 0, which is -2, what I'm actually asking for is the exponent on the factor. Okay, so I asked you, what is the order on this of this 0 of -2? Well, it's 2. What is the order of the 0 of 1 here? It's 1. Okay. Let's take another example. Let's say you have a function f of x equals x times x minus 2 squared times x plus 3 cubed. What is the degree of this function? Well, the 3 plus the 2 plus the 1 will make it 6. So this is a 6-degree function. And what is the order on this? Well, the order on this factor is 1, right? It's x to the power of 1. The order on this factor is 2, and the order on this factor is 3. Okay? And based on the order, you can have kind of a prediction on what the shape would be. So let's say if you had f of x equals x plus 2 squared. This is a parabola. So you would have that any factor that's raised to an order of 2, it will have a parabolic shape at that 0. So the 0 is -2, and it will have the parabolic shape. If you look at our example up here, when the graph passes through this point here, it's going to have, because it is an order of 1, it's going to pass that point like a linear graph. Because this factor has an order of 2, at that 0, it's going to have a parabolic behavior. And because this is an order of 3, it can have cubic behavior at that point. So let's say I was trying to draw a possible graph of this. Okay, it's not the exact graph, but a possible graph would be the zeros are, for this function here, the zeros are 0, 2, and -3. Okay, so that's 0 and 2, and let's say -3. Because it's having a cubic behavior at this point, is going to have passed that point in a cubic fashion. Okay, it's a degree 6 function that has leading coefficient that's going to be positive, so it's going to go from quadrant 2 to quadrant 1. So it's going to start here, and over here at -3, it's going to have like a cubic shape, right? Like y equals x cubed shape. Then at 0, at this 0, it's going to have a linear shape. So it's going to pass through this point like almost like a straight line shape there. And then at 2, because it's quadratic, it's going to have like, it's going to touch this graph, like maybe it could be like looking like this. It could go down and just touch 2 and go up. This could be a possible graph. Okay, so at -3, you have the cubic behavior. At 0, you have a linear behavior because its order is 1 at 0. And at 2, it can have a quadratic behavior where it's kind of parabolic where it touches 2. So the order is very important because it kind of gives us an idea of how that function will be behaving as it passes through that point or crosses that point on the x-axis. Okay. Find the roots or x-intercepts for the function f of x equals 3x cubed minus 4x squared. So let's write that function down and factor it to find its roots. 3x cubed minus 4x squared. We factor out the x squared, which is the greatest common factor of these two terms. And in brackets, we have 3x minus 4. Okay, so to find the roots, set f of x to 0. If f of x is 0, that means x squared could be 0, which means x is 0. Or 3x minus 4 could be 0, which means 3x equals 4, or x is equal to 4 or 3. So you can see here that the zeros are 0 and 4/3. And here, where the 0 is, x squared, the order is 2. So order is 2. So to have a parabolic behavior at 2, at 0, at the value of 0, and at an x value of 4/3, because the order is 1, it's going to have a linear. Let me just spell that correctly. Order is 1. So at 2, I don't know why I'm saying 2 all the time. At x equals 0, it's going to be parabolic. And at x equals 4/3, it's going to be linear because its order is 1. Okay? They didn't ask us that. I just wanted you to remember that. Sketch the graph of the function on the grid provided. So in order to sketch the graph, we could use some points. So we could try to find what the value of the functions at different values of x. So let's say f of -1, that would be -1 cubed times 3 times -1 minus 4, and that would work out to -7. F of 0.5 would be 0.5. They're cubed here, this should be squared. 0.5 squared times -2.5. F of 1 works out to -1. F of 2 works out to 4 times 2, which is 8. So we got some points here for x and y. We just plot those points, -1 and -7, 1 and -1, 2 and 8. Okay, we can see that this function has a degree of 3, and it's a positive leading coefficient, so it's going to be going from quadrant 3 to quadrant 1. So it's going to start here and end here, because it's like the y equals x graph, right? Which has a odd degree and a positive leading coefficient. And at the zeros, which is here, it's going to be like a parabolic shape. And at 4/3, it will have a linear shape. So 4/3 would be approximately 1.3. So 1.3 somewhere here. Okay. Those are the two zeros, 0 and 4/3. So it's kind of very close to each other to see clearly when I plot it, but I'm going to try. So I'm going to start here and go up to 0. And at 0, it's going to be parabolic, so it's going to touch and go down. And then slightly go back up. So it's kind of linear here. And if you can see here, it's a little thick when I'm drawing it. So let me do that again. So it's touching the 0 like that, then going back up like that. Do that. One and -1 is not. Not sure if that's a point, but at this point, it actually is going to go through linear and end up there. I'm not sure about this point. I got to check it. It's going to have, so it's going to be like this. At 0, it's going to have this shape. And let's say this is 4/3. It's going to go back up like that. Okay, so that has the parabolic shape at 0 and a linear shape at 4/3. That's what I wanted to show here. Example 3, write the equation of a polynomial that represents the function shown. There you have a graph of it. You can see how it behaves. So you can see that it has zeros at -3, 0, and 2. And if you look over here at -3, it's kind of passing through like a line, so it's kind of linear behavior. At 0, it has this slight turn like a cubic has, so it's kind of order 3 here. And at the 0, 2, it has like a parabolic behavior, so it's kind of order 2 here. So you're going to say that you have three zeros there. One is x equals -3, and then one x equals 0, and then one at x equals 2. At x equals -3, the shape is linear, right? And so the factor is 1, or the order is 1. At x equals 0, it has kind of a cubic shape, so the order is 3. And at x equals 2, it has a quadratic shape, a parabolic shape, and the order is going to be 2. Okay, so a possible function could be f of x equals, let's use these are all the zeros, so x plus 3, x, and x minus 2. At -3, it's going to be 1 here. At x equals 0, the order is 3, so it should be cubic here. And x minus 2, it's quadratic, so it should be to the power of 2 here. So this could be an equation that represents this particular graph. Okay, and its degree is 2 plus 3, 5 plus 1, 6, which means it goes from quadrant 3 to 4, right? You can see it's like your y equals negative x squared graph. Just put an a value here because we haven't established the exact value of a. We're just doing it based on the factors and the orders of those factors. So let's say I gave you an example, and I gave you a function f of x equals x minus 2 squared times x plus 2 times x plus 3, and I ask you to sketch this polynomial, and I'm giving it to you in factored form. Okay, so you can see that the x-intercepts, or the zeros, are, because in factored form, are 2, -2, and -3. And you can find the y-intercept at x equals 0, y equals, if you put 0 here, you'll get f of x equals 0 minus 2 squared times 0 plus 2 times 0 plus 3. So it's going to be f of x equals 0 minus 2 is -2, squared is 4, times 2 times 3. F of x equals 24. So therefore the y-intercept is 0, 24. So you have the zeros, you have y-intercept. You know it's going to have a quadratic behavior at x equals 2. It's going to be order 2, so it's going to be quadratic. At x equals -2, it's linear. And at x equals -3 also it is linear, because the order is 1 for both of these. Now if you want to know the degree of this function, the degree of this function is 2 plus 1, 3 plus 1, 4. Okay, so it's going to go from quadrant 2 to quadrant 1, because the degree is 4 and the leading coefficient is positive. It's +1 here. So because the leading coefficient is positive and the degree is 4, it's going to go from, it's like y equals x squared, right? It goes from quadrant 2 to quadrant 1. If you want to know exactly how to graph it, we can make a table. Okay, so what we're going to do here is make a table and write down all the factors that we have. So we have x minus 2, which is to the order 2. We have x plus 2 to the order 1. And we have x plus 3 to the order 1. And we'll try to find what happens to the function in different intervals, and see, it gives us more information on how to graph the sketch of this function, or how to sketch the graph of this function. So the zeros are, you're going to go from left to right, -3, -2, and +2. So we want to find, how does this function behave for values of x that are less than this first 0. Then we're going to see what is the function's behavior for values of x that are between this and the next zeros, between -3 and -2. Then we're going to look at what is the behavior of the function for values between -2 and +2. And then finally, what's its behavior for values greater than 2. Okay, so just think of a value that is less than -3, and let's put it here. Let's say -4, right? -4 minus 2 is -6, and when you square that, you get positive number. So that's going to be positive. Take -4. -4 plus 2 is negative. So this would be positive. So all values of x that are less than -3, this would be positive. Put -4 here. -4 plus 3 is -1. So it's, sorry, I made a mistake here. I should have written negative here. And this is also negative. So if you multiply this with this with this, positive with a negative and a negative, what is the function going to be? A positive times a negative is negative, and negative times a negative is positive. So the function is going to have positive values, or the y values are going to be above the x-axis for values of x that are less than -3. Let's just take a value between -3 and -2 to find how the function behaves in that interval. So a value between -3 and -2 could be -2.5. Let's put that in here and see what happens to this. If you put -2.5 minus 2 and squared, you'll get a plus, right? It's a positive number. If you put -2.5 plus 2, you're going to get a negative. -2.5 plus 3, you're going to get a positive. So when you multiply a positive and negative, you get negative. Negative times positive is negative. So the values of the function, or the y values between these two intervals, will all be under the x-axis. They will all be negative. Then think of a value between -2 and +2. Let's take an easy number like 0. 0 minus 2 is -2. You square that, you get a plus. 0 plus 2 is positive. 0 plus 3 is also positive. So when you multiply 3 positives, the function is positive. So between -2 and +2, the function is above 0. And for values of x greater than 2, let's take a value like 3. 3 minus 2 is 1. 1 squared is positive. 3 plus 2 is positive. 3 plus 3 is positive. And the product of these three is going to be positive. So now we have all this information. We can easily sketch now the possible graph of this function. So it has a 0 at -3. It has a 0 at -2, and then it has a 0 at 2. We know that it's going to go from quadrant 2. So it's going to start here. And for values of x less than -3, the function is positive. So and at x equals 3, it's linear, so it has to cross it. So we'll start here, we'll go there, and cross it to show that it's having a linear behavior at -3. Then between -3 and -2, the function is negative, right? So I'm just going to highlight here. This was positive, that's why it's positive. And between -3 and -2, the function is negative. So all values of this graph will be negative. And what happens at -2? What is the behavior? It's linear, so it has to cross it. Okay, so over here, at some point, it's going to, sorry, let's use the same coloring. It's going to cross and be linear at -2. Then it's going to go up to its y-intercept. Let's say this is our 24. It's going to go up to 24 and come back down. And then we're going to know that at x equals 2, the function has a quadratic behavior. So it's just going to touch the graph at x equals 2. So at x equals 2, the function will be quadratic. And we know it has to end back in quadrant 1. So it goes from quadrant 2 to quadrant 1. It has zeros at -3, -2, and +2. A linear function, a linear behavior at -3, a linear behavior at -2, and a quadratic behavior at +2. And we know that at the intervals of x less than -3, the value of the function is positive. Between -3 and -2, the y values are negative, as we see here. For values between -2 and +2, they're all positive. So this part of the graph is all above the x-axis. And then after 2 also, they're all positive. So this part is also above the x-axis. So that's how we draw a sketch of the function. Okay. To summarize, let's say you have a function like this. You can see that these are the zeros, -2, -1, 4, and 5. Its degree is 1, 2, 3, 4. And the leading coefficient is positive, so it's going to go from quadrant 2 to quadrant 1. And their orders are all 1. So through each 0, it's going to just be linear, right? So it's going to be crossing here, crossing here, crossing here, crossing here, like that. So if any of the factors of a polynomial function are linear, then the corresponding x-intercept is a point where the curve passes through the x-axis. The graph has a linear shape near this x-intercept. So all of them being order 1, the graph is, they're going to have linear behavior here, linear behavior here, linear, linear. Okay, so it's crossing through like it was a straight line at that x-intercept. Another case you can have, case 2, is when you have a degree that is odd, so 2 + 1, 3. Leading coefficient is positive, so it has to go from quadrant 3 to quadrant 1. And you can see the order on this x-intercept is 2. So at x equals -3, it is going to have a quadratic behavior. The order on this factor is 1, so at x equals 2, it's going to have a linear behavior. So you can see there at -3, it just touches there, has a parabolic shape, and then at 2, it has a linear shape. So if any of the factors of a polynomial function are squared, then the corresponding x-intercepts are turning points of the curve, and the x-axis is tangent to the curve at these points. So the x-axis is tangent to this curve, and you can see that it's like there's a turning point happening at x equals -3. The graph has a parabolic shape right here. Third case, y equals 1/5x + 3 cubed times x - 1. The degree is 4. It's a positive leading coefficient, so it has to go from quadrant 2 to quadrant 1. The 0, which is x equal to -3, has an order of 3, so it's going to have a cubic nature at x equal to -3. The order of this factor is 1, so it's going to have a linear nature at x equals 1. Okay, so for this factor here, or this 0 here at x equals -3, it's going to have a cubic behavior, which is why you can see it's just, having that cubic shape here. If any of the factors of a polynomial function are cubed, then the corresponding x-intercepts are points on the x-axis, where the x-axis is tangent to the curve and also passes through the x-axis. The graph has a cubic shape near these x-intercepts. So it crosses the x-axis and has a cubic behavior at x equals -3, whereas at x equals 1, it has that linear behavior. So in summarizing, to find the equation of a polynomial function in factored form, you're going to substitute the zeros into the general equation of the appropriate family of polynomial functions. Determine the order of each factor by looking at each 0 on the graph. The order of the 0 is the exponent on the factor. Substitute the coordinates of an additional point x and y if you wanted to solve for the leading coefficient and find the exact equation of that function. So now you want to practice these questions.